Okay, so this video is taking a look at some of the week one probability problems and just sort of explaining them as I go. I'm not going to go through every single problem, although I have uploaded every single solution, just not with an explanation every single one, but I'll go through a couple of the probability problems now. So let's first take a look at problem number 2. In this problem, we had a group of 500 students, and we're told that 44% equals male, 56% is female, and then a bunch of stats about hair color. We got 15% as red hair, 35% as blonde hair, 40% brown haired, and 10% black hair. And I've even given event names. This is event M, this is event F. Red hair was event R. Blonde hair is event B. Brown hair, because I already used B, we'll use W, just a letter of brown. And black, we already used B, so we'll just use K for the letter at the end of black. All right, so this is basically the given information. Some of the questions, how many boys? We are going to take the probability of choosing a male student, and we are going to multiply that by the number of total students. And we'll just use our calculator for that, 0.44 times 500, and that's 220. Similar for part B, similar for part C. Part D, let's take a look at that. How many redheaded females? Now, we're told that the probabilities are independent, so we can use the rule about independent probabilities where we multiply the individuals. That means the probability of red and female is equal to the probability of red times the probability of female. So that is going to be the probability of red. That was 0.15, 15%. And the probability of being female is 0.56 or 56%. So the probability of getting red and female is 0.15 times 0.56, which is 0.084. So that represents, if we move the decimal 2 places over, remember the conversion, that is equal to 8.4% chance of getting a redhead and a female. And then part E, take this one step further. We're looking for the number of, it's not how many, it's probability. Last problem. For this one, how many? Okay, so what we're going to do is take the probability of being male, which is 44%, the probability of being black-haired, which is 10%. Okay, these guys are independent, so the probability of being male and black-haired is going to be the product of the two of these. I can't even believe I used my calculator for that, but that's 0.044 or a 4.4% chance. Okay, but if we want to figure out the number, we're going to take that number and multiply it by the entire set of students, which is 500. To get the total number, which is 22. All right. Okay, to take a look at a couple of the dice rolling probability problems, just in case you had any issues. Let's take a look at, let's see here now, probability for both dice. Let's take a look at number 5. Okay, now there are a couple parts. I'm assuming you were able to get 2, 3, and 4. So number 2, the probability of the first die is 4. First die is 4. Was 6 out of 36. In number 3, the probability of the second die is 4. Was also 6 out of 36. And for number 4, the probability of both die being 4 was 1 out of 36. Now, problem number 5 is asking, are these two events independent? So if independent, then the probability of first die 4 times the probability of the second die 4 will equal the probability of first die 4 and second die 4. So let's see, is that true? Is it true that 6 over 36 times 6 over 36, is that equal to 1 over 36? Well, at first glance, you might think no, but let's not be too hasty. 6 over 36, we can simplify that to 1/6, and another 6 over 36, that's 1/6. And when multiplying fractions, you multiply numerators and multiply denominators. And 1 times 1 is 1. 6 times 6 is 36, so they are. And a very informal way of thinking about it, if you roll 2 dice, you know, what lands on one die does not depend on what the other die comes up. I mean, we're assuming here that they're not like interfering with each other in midair. So, I mean, you could roll one die over here on the right side of the room, roll the other die on the left side of the room, and one has nothing to do with the other. This just sort of mathematically shows that principle. If the two events are independent, then the product of their individual probabilities is equal to the probability of them both happening at the same time, or the intersection. What else kind of looked a little hard here? The probability of... let's look at maybe number 14. There are some individual parts here. What is the probability of the sum of... The probability of the sum is even and the product is odd. So let's take a look here. Probability of sum even. Okay, and if you added all of those up and then counted, the probability of the sum is even, by the way, which is problem number 10, is 50%, or 18 over 36. The probability that the product is odd which is number 8. You just kind of count the list. That is 9 out of 36. And these simplify. (18 over 36 simplifies to 1/2. 9 over 36 simplifies to 1/4. And then the probability of the sum is even and the product is odd. So if we go to our sample space and count those, so again, sum even and product odd, we should get 9 of those. Let me just double check. So the sum is even, 1 plus 1. The sum is 2. The product is odd, 1. So there's one of them. 2, 3, 4, 5, 6, 7, 8, 9. Just those 9. Okay. So truly, that last counting I did is actually the answer to number 14. What I really did all that other work for is to look at number 15, which is actually what I meant to do the whole time. Are these independent? Well, if independent, then the probability of sum even times the probability of product odd would equal the probability of sum even and intersect product odd. So let's see if this is true. The probability of the sum is even, that was 1/2, is 1/2 times product odd, 1/4. Does that equal the probability of them both happening? Let's see. Well, multiply numerators, multiply denominators. 1 times 1 is 1. 2 times 4 is 8. Does 1/8 equal 1/4? No. So that means these are not independent. And let's think about that logically for just a moment here, and then we'll finish the video. What was the question asking in number 15? Are the events the sum of the two dice even and the product of the two dice odd? Are those independent? It turns out no. Those two events actually do depend on each other. You can't get a sum that is even. Well, actually, I'm saying this backwards. Let me rephrase the way I was saying that. What are the ways that you can get the sum is even? You can get a sum with either an even plus an even or an odd plus an odd. However, if you add an even plus an odd would be odd. An odd plus an even would also be odd. So to get the sum even, there's only two ways that you can do that, is if you have two even numbers when you roll the dice, or two odd numbers. You add two even numbers, you get another even number. You add two odd numbers, you get an even number. You can't roll one even and one odd. If you add those two together, then you get an odd sum. Okay, and now let's take a look at product odd. Okay, if I get an even and an even, if I get an odd and an odd, if I get an even and an odd, if I get an odd and an even. Sorry, I wrote that backwards. Okay, if I get two numbers that are both even and I multiply them together, do I get an odd number? No. If I multiply two odd numbers, do I get an odd product? Yes. If I multiply an even times an odd, do I get an odd product? 2 times 7 is 14. That's an even number, so that's not an odd product. And same thing here. So the only situation where I would even have the product of two numbers as being odd is if both of the individual numbers are odd. And that's half of the situation when I get an even sum. So because the only time you could ever get an odd product is when both of these dice are odd, these two probabilities depend on each other. I could never get an odd product if I had an even and an odd. So just the fact that this one event happened, it gives me a 50-50% chance of this other event happening. If this event doesn't happen, there's no way I could get this event to happen. So these two things depend on each other. Yeah.